Hello and welcome. In this video, we're going to build on what we covered in the last video about U-substitution, but we're going to talk about what happens when all of your x's don't divide away after you substitute in what u is equal to, and that's called the change of variable. We're also going to talk about how to use U-substitution with a definite integral, so when there are bounds on the integral. So let's go ahead and dive right in. So why don't you go ahead and try and do U-substitution on this indefinite integral here using what we already know, and then see if you have an issue when you're doing that. Then unpause the video and see how you did. So if we are solving this, we would let u equal the inside function, which in this case is x minus 1, which means that du would just be equal to dx. So we would end up, and I'm going to just jump down here, with the integral of x times what we just decided that u was. Actually, I'm going to use black, times u to the power of 1/2. I'm just going to manipulate that radical there. And then du. So hopefully that you noticed our issue is right here. Our issue is that we have an x still. It hasn't simplified out like it did in the previous problems in the earlier video that we made. We still have an x here that needs to go away in order for us to integrate with respect to u. So, do you have any idea how we can manipulate this so that we don't have x's anymore? Well, some of you may have noticed that we do have a relationship that we defined between x and u. We could just solve this for x. So that would mean that x is equal to, if I add 1 to both sides here, u plus 1, which means now I can replace this x with u plus 1. I still have u to the power of 1/2 and du. And now, in order to evaluate this, I can actually multiply, since these are all in terms of u, I can multiply or distribute u to the 1/2 out. So this is going to give me the integral of u to the first plus 1/2 is u to the 3/2 plus u to the 1/2 du. And now I can just evaluate each of these antiderivatives. So if I add 1 to 3 over 2, I get 5 over 2. So there's going to be a 2/5 in front. If I add 1 to 1/2, I get 3/2. So there's going to be a 2/3 in front, plus c. And then we want to make sure that, as always, we substitute back in what we know that u is. U is equal to x minus 1. So this type of u substitution has a special name. It's called change of variable. And the reason is because you need to change your x to be in terms of u. And we always change x to be in terms of u, but not in the same way that we normally do by just using direct u substitution, but actually having to solve for x. So we tried to do u substitution, and we still had this issue of having an x here. So we had to manipulate what u is equal to so that we could rewrite x in terms of u. Then we could go through the exact same process that we went through before. So let's go ahead and look at some more examples of this change of variable u substitution. Okay, so here we go on number 1. The most inside function that I see is 2x minus 1. So I'm going to say let u equal 2x minus 1, which means that du is 2 dx. So dx is equal to du divided by 2. So if I rewrite the integral, I'm going to have the integral of x, this x up here hasn't changed, times u is 2x minus 1, and I'm going to just write that as to the negative 1/2 power to deal with my square root in the denominator. And that's going to be multiplied by du over 2. Now here's where I have a different situation than we did in the last video. My x here isn't dividing out with my du over here, and that's what's indicating to me that I need to use my change of variable in order to evaluate this. So I'm going to go back up to where I identified what u was, or I defined what u was, and I'm going to solve for x. So if I add 1 to both sides, I get that u plus 1 is equal to 2x. So x is going to be equal to u plus 1 divided by 2. And I'm going to substitute this in for the x that I still have here. So this is going to become the integral of u plus 1 over 2 times, and this is supposed to be a u to the negative 1/2 power times du over 2. Now I'm going to simplify anything that I can simplify here. Well, the first thing that I notice is that I have 2 2's in the denominator. So since I don't want to confuse myself with fractions while I work through this integral, I'm just going to take them both out. 1/2 times 1/2 is 1/4, and based on properties of integrals, I can just pull that out in front. Now, if I combine my u terms, I have u to the negative 1/2, and I'm going to distribute that here. U to the negative 1/2 times u to the first is u to the 1 minus 1/2, or u to the 1/2 power, plus u to the negative 1/2 power du. Now I'm going to go ahead and I'm going to evaluate this integral. So u to the 1/2, if I add 1, is going to become u to the 3/2 divided by 3/2, or times 2/3, plus u to the negative 1/2 is going to become u to the positive 1/2 divided by 1/2, or times 2, plus some c value. And then I'm going to go ahead and simplify. I'm going to multiply my 1/4 in, and I'm also going to rewrite, or I'm going to re-plug in what u was. So 1/4 times 2/3 is going to end up giving me 1/6 times not u to the 3/2, but what was u? It was 2x minus 1. Plus, if I multiply 1/4 by 2, I get 1/2, not times u to the 1/2 power anymore, but substituting back in what u was equal to, 2x minus 1, plus my c value. So really similar to what we were doing last class, with the exception of now we have to manipulate a little bit more to get everything to be in terms of u and to not have any x's left over. So on number 2, I'm going to go ahead and let u equal 2 minus x. That's going to make du negative dx, or dx is equal to negative du. So if I tried to rewrite my integral now, I still have x plus 1. I now have u to the power of 1/2, and I have negative du. So again, there isn't anything that is allowing me to get rid of this x plus 1, so I need to go back to my u and I need to solve for x in that u statement. So if I solve for x, if I subtract 2 and then divide by negative 1, I'm going to get that x is equal to 2 minus u. So I'm going to substitute that in just for the x piece here. So the integral of 2 minus u plus 1 times u to the power of 1/2 times negative du. And I'm going to simplify just one more time before I integrate. This is going to become negative u plus 3, negative u plus 3 times u to the 1/2 power du. And I'm going to actually, this negative sign, I'm going to put it in front here. And now I'm going to simplify. So negative times a negative is a positive, and negative u to the first and u to the 1/2 is going to become positive u to the 3/2. Minus, because I'm distributing this negative sign, 3u to the 1/2 power du. And now I can go ahead and integrate. U to the 3/2 is going to become u to the 5/2 with a 2/5 in front, minus 3 times u to the 3/2 with a 2/3 in front, plus c. And then I'm going to go ahead and simplify and plug my u's back in. So 2/5 times 2 minus x to the power of 5 over 2 minus 2 times 2 minus x to the power of 3 over 2 plus some arbitrary constant, plus c. So hopefully you're starting to feel a little bit more confident with this topic. I'm going to go ahead and put up a couple new examples for you to work through on your own. So I encourage you, if you're feeling confident, go ahead and pause the video and work through these on your own, and then unpause the video and see how you did. So I'm going to go ahead and define my u, my du, and then see where I'm at when I substitute into my integral. So after I define u and I find du and I do substitution, this is where I'm at. For both of these problems, I have this issue that I have an x here that I need to get rid of. So I'm going to go ahead and solve for x here. X is going to equal u minus 4, so that's going to get plugged in here. Over here, x is going to equal u minus 1, and that's going to go ahead and get plugged in here. And then if we put everything else back in there, now before we find the antiderivative, we're going to go ahead and simplify what's here. So I'm going to distribute u to the first times u to the negative 1/2 is u to the positive 1/2 minus 4u to the negative 1/2 du. And if I integrate that, I'm going to get u to the 3/2 with 2/3 in front minus 4 times u to the 1/2. And I'm going to divide that by 1/2 or multiply it by 2 plus c. And then lastly, I'm going to make sure that I substitute back in what u is, which in this case was x plus 4. And there is my evaluated answer. If you haven't already finished number 4 on your own, I encourage you to do so now. So here is what you should end up with on number 4. So distribute up here so that you can get to this line, then use the power rule so that you can get here, and then substitute back in what your u value is so that you can get to our final answer. Let's look at one more example in sort of a different form, but the same math that we have already been doing before we start talking about definite integrals. Here we go. So number 5 says to solve the differential equation. A differential equation, which we're going to define in more depth in a later unit, is just an equation that involves a derivative. So before we can actually integrate, what we need to do is separate the dy and dx. So we're going to go ahead and leave dy over here, and we're basically going to multiply both sides by dx, if you want to think about it that way. So that gives us x cosine of x squared dx. And to get rid of the dy and the dx, we're going to integrate both sides. So if I integrate dy, I just get a y. And now we're going to have to use u-substitution to manipulate this portion over here with the x's. So I'm going to let u equal x squared. So du is 2x dx. So dx is equal to du divided by 2x. So I'm still going to have the integral. I still have an x and a cosine, but now I have a cosine of u. And this is being multiplied by du over 2x. So this is more like from the last video where our x's are going to divide out. We don't have to do change of variable here. So this is going to give us y equals, this 2 down here is in the denominator. I'm going to take that out in front of the integral of cosine of u du. And what do I integrate to get cosine? Or what do I get when I integrate cosine? I get sine of u plus c. And then we're going to substitute back in what u was x squared. So we're going to get the equation y equals 1/2 times sine of x squared plus c. So now that we have wrapped up change of variable, which is a situation that occurs when our x's don't divide out and more needs to be done in order for us to use u-substitution, we're going to talk about what happens if we use u-substitution with a definite integral, if there are bounds on the integral. So let's go ahead and jump into that. So as a reminder, a definite integral is an integral that has bounds. It has numbers on the integral. U-substitution is something that changes all of the things that are in terms of x to be in terms of u, which means that if we have bounds, when we change our variable to be in terms of u, we also need to change our bounds to be in terms of u. So let's go ahead and look through this step by step. If we were looking at number 6 and there were no bounds, we would start by saying let u equal x squared plus 1. So du would equal 2x dx. So dx would equal du over 2x. So if I was going to rewrite the integral, I'm going to leave the bounds off temporarily. This is the integral of x times u to the third power times du over 2x. And these x's are going to divide out. So I'm going to have the integral of u to the third du. However, it is not going to be the integral from 0 to 1 anymore because 0 to 1 are the bounds that we're dealing with when we have x. So what we need to do is notice that if x is 0, what does that mean for u? If x is 0, we just plug that in here. 0 squared plus 1 is going to be 1. So if x is 0, u is 1. That means my lower bound is going to change to become 1. Well, what happens if x is the upper bound? The upper bound is 1. If x is 1, again, plugging this in over here, 1 squared plus 1 is going to be 2. Our upper bound is going to be 2. So all we're doing is changing one more thing to be from in terms of x to now be in terms of u. But I almost lost my 1/2 here. This 2 I'm going to pull in front of my integral here. So now I'm going to go ahead and I'm going to evaluate this integral. I'm going to leave my 1/2 here. If I integrate u to the power of 3, I get u to the power of 4 divided by 4. And this is being evaluated from 1 to 2. So I don't ever have to, when I have bounds on my integral, when I'm looking at a definite integral, I don't have to substitute back in what u is equal to because I already changed my bounds to also be in terms of u. So all I need to do now is plug 2 in, plug 1 in, deal with that math inside, and then multiply that by 1/2. So let's go ahead and do that. 1/2 times 2 to the 4th is 16. 16, so actually I'm going to write this step. 2 to the 4th divided by 4 minus 1 to the 4th divided by 4. This is going to be 1/2. 2 to the 4th is 16. 16 divided by 4 is 4 minus 1 to the 4th. This is going to be 1/2 times 16 over 4. I guess I could have left it as 16 over 4 because then I have a common denominator, 15 over 4. So this is going to be 15 over 8. So when we have a definite integral, we actually only have to deal with x at the very beginning of the problem. And once we have gotten rid of x and changed our bounds, we can work through the rest of the problem in terms of u. So let's look at another example. Let's let u equal 1 minus x squared. So du is going to be negative 2x dx. And let's go ahead and write the integral. I'll come back to the bounds in just a minute. This is going to be x times u to the power of 1/2 times du divided by negative 2x if I solve this for dx here, which means my x's are going to divide out here. So I'm going to have negative 1/2 times the integral of u to the 1/2 du. But let's deal with our bounds. If x is equal to 0, and I plug that in here, I get 1 minus 0, which is 1. So if x is 0, u is 1. If x is 1, and I plug that in, u is going to be 1 minus 1 squared. U is going to be 0. Now you may have noticed right here that the bounds of our integral are backwards. The smaller number is typically on the bottom. And if you remember from earlier in this chapter, that's an easy fix. All we need to do is change the sign here and we can flip them back. If you didn't notice that, that math would have happened naturally as you worked through it. You would have gotten to the same answer. The negative sign would have just come into play in a different way. But I am going to change it because I did notice. So I'm going to rewrite this as positive 1/2 times the integral from 0 to 1 of u to the power of 1/2 du. And if you didn't see that, that's okay. I'm hoping that you see it now, but you still probably would have gotten to the same answer. So let's integrate. U to the 1/2 power is going to become u to the 3/2 power, and that's going to get multiplied by 2/3, and that's going from 0 to 1. I'm going to deal with this scalar. 1/2 times 2/3 is going to become 1/3 times 1 to the 3 over 2 minus 0 to the 3 over 2. Well, 0 to the 3 over 2 is just 0. 1 to the 3 over 2 is just 1, so this is going to become 1/3 times 1, which is just going to be 1/3. Let's look at some more problems. Okay, I'm going to encourage you to just change everything, including the bounds, to be in terms of u, and then to unpause the video and see how you did. So here's everything from the first part of the lesson, but now let's go ahead and change our bounds. If x equals -2, then u is going to be -2 to the third, which is -8, plus 8, which is going to be 0. If x equals 1, then u is going to be 1 to the third, which is 1, plus 8, which is 9. All right, I encourage you to pause the video and finish this integral off on your own, and then unpause the video to see how you did. So u squared is going to become u to the third over 3, multiplied by the over 3 that was already there, and I'm actually going to pull that scalar out. So 1/9 times u to the third, being evaluated from 9 to 0. So 1/9 times 9 to the third divided by 0. Now notice, I'm not actually going to figure out what 9 to the third is because I'm going to divide it by 9 or multiply it by 1 over 9. So that's going to just become 9 squared. So this whole thing is just going to equal 81. Now, I'm really going to encourage you to pause this video and work through the whole thing on your own. But I'm actually going to make one adjustment first. I meant to do this before I started this video. We're going to change these bounds to be from 0 to 2, just so we don't get quite such large numbers. So the integral from 0 to 2 of what you see there. Unpause the video once you've worked through that. So hopefully you've had a chance to work through this. Once we get rid of all things related to x, we should end up with 2/3 times the integral from 1 to 9 of u to the 1/2 power du, which is going to become 2/3 times u to the 3/2 multiplied by 2/3, evaluated from 1 to 9. So I'm going to go ahead and take 4/9 out. 9 to the 3 over 2 minus 1 to the 3 over 2 if I substitute in. So this is 4 over 9. 9 to the 3 over 2 is the same thing as the square root of 9 cubed. Well, the square root of 9 is 3. 3 cubed is 27. 1 to the power of anything is just going to be 1. So this is going to be 4 times 26 over 9, which if we simplify is going to become 104 over 9. All right, we're going to do just a couple more examples and then we're going to wrap up this video. Okay, if you're feeling confident, see how you can do on 10 through 12. Otherwise, I'm going to get things set up and then work through the new parts with you. So here we go. We're going to let u equal 2/3 x, so du is 2/3 dx. So dx is 3 over 2 times du, and I'm going to just pull that scalar out in front of the integral. And now we have the integral of cosine of u du. If x is equal to 0, then u is going to be equal to 2 times 0 over 3, which is also 0. If x is equal to pi over 2, then u is going to be equal to 2 times pi over 2 divided by 3, which is just going to be pi over 3. So 3 over 2, if we integrate cosine of u, we get sine of u, evaluated from 0 to pi over 3. So 3 over 2 times sine of pi over 3 minus sine of 0. Sine of 0 is 0. Sine of pi over 3 is root 3 over 2. So this is going to be 3 over 2 times root 3 over 2, or 3 root 3 over 4. All right, let's get through number 11. So here's our simplified integral with u-substitution. These 6x's are going to divide out, and let's go ahead and find our new bounds. If x equals 0, then u equals 0. 3 times 0 squared is still just 0. If x equals the square root of pi, then u equals 3 times the square root of pi squared, which is just going to be 3 pi. If I integrate sine of u, I get negative cosine of u, because I'm asking myself, what did I take the derivative of to get positive sine? That would be negative cosine. And I'm going to evaluate this from 0 to 3 pi. I'm going to take the negative out. So negative times cosine of 3 pi minus cosine of 0. Cosine of 3 pi is 1. And cosine of 3 pi is negative 1. And cosine of 0 is 1, but I'm subtracting that. So this is going to be the opposite of negative 1 minus 1. So this is going to be 2. Okay, last but not least, number 12. If f prime of x is equal to 6x times the square root of x squared minus 3, and f of 2 equals 5, so we have an initial condition, determine f of x. So we know that f of x is going to be equal to the integral of 6x, and I'm going to rewrite this with rational exponents. And this is not something I can integrate in the state that it's in, so I'm going to go ahead and use U-substitution. I'm going to let u equal x squared minus 3, so du is 2x dx, so dx is du divided by 2x. So this is going to be equal to the integral of 6x times u to the 1/2 power times du over 2x. 6x and 2x are going to divide to just be 3. So 3 times the integral of u to the 1/2 du, or 3 times u to the 3/2 times 2/3 plus c, which is going to be 2, and I'm going to plug u back in. That doesn't look much like anything. 2 times u, which was x squared minus 3, to the 3/2 power plus c. Now I need to use my initial condition to figure out what c is. So with the point 2, 5, I'm going to have that 5 is equal to 2 times 2 squared is 4 minus 3 is 1. So 2 times 1 plus c. So c is going to be equal to 3. And then we can rewrite f of x as 2 times x squared minus 3 to the 3 over 2 plus 3. And that is our function. So big ideas in this section. Using U-substitution and having to change our variable, not only in the way where we first define what u is, but also that we manipulate that equation so that we can substitute something in for x if we have a problem with a different x as well. Then we built on that idea more by talking about how do we evaluate a definite integral. So sometimes we may also have to change the bounds to be in terms of u in order to evaluate a definite integral. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.